Oh,
Okay, good afternoon. This is Oceanography, OCE 4008. We're concluding our lecture this week on Chapter 3 material concerning plate tectonics, the theory of plate tectonics, which determines how ocean basins are formed, how the surface of the Earth develops over time due to the processes of plate movement. So we have established that the Earth is 4.7 billion years old, and that throughout this incredibly long history, the surface of the Earth, which is a thin layer of lithified material floating on, or floating in quotes, on a much larger volume of ductile material called the mantle, and that over time on this lithospheric surface, the layers of material have been accumulating, so that we can dig back, if we go back through time, we can discover all of the layers of Earth history. And so we want to try to understand how the Earth is behaving over this period. And so the theory which ties this together is this theory of plate tectonics. And it builds on the idea that we have a layered Earth, that we have this outer lithosphere floating on a ductile mantle, and that the heat, the tremendous heat in the interior of the Earth is moving material upward in gigantic induction spheres or cells. And that as this material moves up, it causes changes on the surface of the Earth. Specifically, it forms new ocean crust at lower spreading centers. And the formation of this crust is apart the continental material. The continental material is less dense, and so it's floating again in quotes, at a higher level than the ocean crust. And so the formation of new crust pushes apart these continental land masses. So the continental land masses are thick, they have deep roots, they have an average thickness of about 35 kilometers. They are primarily formed from granitic material, which is slightly less dense than the basaltic material, which comprises the ocean crusts. So prior to the late 1950s, the idea of the Earth as a dynamic entity, and the surface of the Earth as an area which was undergoing constant change, was not widely accepted by scientists, by Earth scientists. The prevailing view at that time was that the Earth was cooling, so that the scientists recognized that the center of the Earth was warm, probably very warm, and they speculated that that heat was dissipating over time, and that with the dissipation of heat there would be a loss in volume, so that a shrinking, cooling body tends to shrink in size, and the idea was that the shrinking of the Earth was causing wrinkle-like features to form on the surface, and that these ripple-like features or wrinkle-like features were responsible for generating what could be observed: continents, oceans, valleys, etc. Well, this began to change, first with the proposal by Alfred Wegener, the German scientist, who suggested that their continents were actually drifting apart. And he proposed different lines of evidence to show that there had been connection between continents that were now separated. And he proposed that they had been joined together in geologic history, and that by some process they had become separated and to move across the surface of the globe. Well, this was a revolutionary idea. It was not widely accepted. In fact, it was ridiculed by the prevailing scientists of the day, and Wegener went to his death, not having been able to establish this idea of continental drift as a mechanism that was actually happening on the Earth. Well, and one of the reasons that he failed to do this is that although he had a story which explained the things that they were able to observe, the existence of continents, the fact that there were shared fossil relatives on different continents that were now separated. But the mechanism that he proposed, which was that the continents were drifting across the surface of the planet due to the centrifugal forces of the Earth's orbit and the Earth's rotation, there simply wasn't enough energy in that centrifugal force to explain these giant movements and this, vast dislocation of rocky material that would have to take place in order for that to happen. Well, if we move ahead in time to a scientist named Tuzo Wilson. So Wilson, starting in the 1960s, looked at the same things that Wegener had looked at, and he came to a similar conclusion, namely that the continents were moving about, but he proposed an entirely different mechanism that would explain how this motion could take place, and that this mechanism was provable by putting together observable facts about different processes. And so we start with the idea that there's a puzzle piece. The American continent and the European, African continents fit together. Well, somehow they've come apart and drifted apart. So how does this drifting or this movement take place? And well, the first thing he had to do was to establish that the continents were in fact moving over time, and that the cause of this movement was that there was new plate material, new surface crust was forming between the existing continents. Well, how to prove this? The first question is proving that the plates were in fact moving. And he proposed this by looking at the theory of, he proposed this, or he tried to demonstrate this by looking at hotspots and by analyzing different data. And the development of the plate tectonics theory was enabled by various key technologies. Seismics, as we suggested, seismic makes it possible to detect, to measure, to categorize large-scale earth motion that generate earthquakes. So earthquakes essentially can be telescopes that allow scientists to look into the interior of the Earth. Another key technology was the ability to measure ocean depth over large scales, so that distinct features of the ocean floor can be resolved even though they are thousands of meters beneath the surface and very difficult to observe with standard technology. Magnetometers, the ability to measure the magnetic charge of the seafloor, was another enabling technology. And finally, we'll see that submarines, the ability to dive down and observe the seafloor at these dynamic centers, was the final nail in the coffin, or the final key to understanding that plate tectonics was in fact occurring. So the seismograph is this ability to measure in a continuous line the depth of the ocean. And as we talked about on Tuesday, this is a precision depth recorder that's recording the ocean depth over a course. It's about it's like about 150 miles or 160 miles of distance here. And across this area, we see that the ocean floor is not smooth and uniform, as was the idea at the time, but in fact has these features of high relief, including this valley-like feature lying between two mountain ranges. So Tuzo Wilson proposed that new seafloor was forming along these features. And this feature in the middle of the Atlantic Ocean is called the mid-ocean ridge. Okay, well, if the mid-ocean ridge is the location where new seafloor is being generated along this feature, then this new seafloor, when it comes out, is rocky and rigid. And so it can't move without cracking, without breaking. It comes out and it moves apart, but as it moves, there has to be an accommodation of the shape of the globe to allow this motion to continue. And so what Wilson observed was that along this feature, that he suggested was the origin of new ocean plate in the middle of the Atlantic Ocean, that there were faults, transform faults. And these transform faults occurred as the seafloor was moving apart. So transform faults accommodate this shift or this growth of new ocean seafloor along the mid-ocean ridge. And according to the theory and according to understanding of how physics works, we could predict that these transform faults would have to be at right angles, more or less, to the axis of the mid-ocean ridge. And so Wilson, looked at the same data that everyone else had done and said, well, okay, if we try to understand these in terms of this theory that I'm proposing, we can see that this idea is a confirmation of that. Okay, so the other technology that confirmed that this was happening was the ability to measure the magnetic charge recorded when the new seafloor was formed. So let's think about this. There's volcanic material erupting. The eruption of this volcanic material generates new ocean crust, new ocean plates, and that while the magma, the lava, is cooling, it retains the magnetic orientation that's present on the Earth at the time of formation. Well, as we have established, Earth is a bipole. There is a magnetic north and a magnetic south, and these are fixed in short-term periods. But over million-year cycles, the magnetic poles, the magnetic field shifts, so that what was previously north becomes south, and south becomes north, etc. And the minerals, the iron minerals in the new rock retain that orientation, and then when the rock solidifies, those orientation, those little compass points are preserved. So by collecting samples and by measuring the orientation of the minerals in those samples, we can see which way was north, which way was magnetic north when the rock was formed. And so this key piece of evidence showed that there was an alternation. And this alternation corresponded to what was known about changes in the Earth's dipole. And so the mid-ocean ridges and the rocks adjacent to the mid-ocean ridges record a parallel series of magnetic reversals. And so this was also confirmation that new material was forming and that it was moving apart, generating new seafloor. Okay, well, if new material is forming and this continents are breaking apart, there must be some mechanism or some process that breaks the land masses apart in the first place. And Wilson proposed that this was called rifting. So rifting is in Wilson's concept was that due to pressure from the magma acting underneath continents, continents break apart. The magma pushes up, and the continental crust can't accommodate that, and it breaks apart and forms a crack in the continent. And that over time, millions of years, tens of millions of years, this crack widens and widens. First, there's a linear sea, then there's a much broader sea with a mid-ocean ridge down the middle. And so this rifting process is essential to transforming a continent into an ocean basin that separates two previously connected continents. Okay, well, if this is happening, can we find evidence of rifting at different periods in time? And the answer to that is yes. If we look at an area of active rifting, and this is west coast or the east coast of Africa, there's an example of two rift centers. Now, you can confirm the way that continental drift and continental rifting happens with a simple experiment. If you take the peel of an orange, take an orange peel and lift it off the orange so that you have the orange peel in your hand. And then take your finger and force it up through the orange so that the orange peel has to break apart to accommodate the pressure of your finger. What you'll find is that the orange peel will break apart in a fault that has a star that has 3 points. And that's because that's the simplest, most efficient way for that breaking to happen. So that's how ocean rifting or continental rifting takes place. There's a 3-pointed star. And typically what happens is that one leg of the star doesn't continue to rift, and that the separation occurs along the remaining 2 points. And that's what we see at this, the place where this rifting occurs is called a triple junction. So one of the most prominent triple junctions on the planet is the triple junction that occurs at the origin of the Red Sea and the Gulf of Aden. So these are the 2 points. The Red Sea is a newly formed rift, and that over time the Arabian Peninsula is going to separate from the African Peninsula, and then millions of years from now, hundreds of millions of years from now, there'll be an actual ocean basin between these 2 land masses. And then there's a rift valley in Africa, and this is a famous rift valley. This is where Lake Victoria, Lake Tanganyika are located. But this rift zone didn't continue to break apart. So this is the triple star. You can see these, and all along this rift, you can see evidence for continuous seafloor spreading because of the existence of transform faults that run at roughly right angles to the rift. And so here is a picture of the Rift Valley in Ethiopia, and you can see this deep crevice opening up in the ground. Well, this crevice was formed, a few 10 million years or so ago, and for whatever reason, it stopped spreading, and the spreading between the Red Sea and the Gulf of Aden is where the seafloor spreading has continued. Okay, so that was another piece of confirmation, this idea that there was rifting, and that the rifting formed allowed new ocean crusts to form, and that as the ocean crust formed, it pushed the continents apart. And so, Wilson's idea led to the understanding that the surface of the Earth, the lithosphere of Earth's surface, comprises a whole series of plates. Oceanic plate, which is constantly being renewed along the ocean ridges, and then subducting under continents. We'll get to that in a second. So there's ocean plates, and then there are continental plates. And as we said, the ocean plates have a very different characteristic from the ocean plates. And so these are the boundaries. This is as we conceive in present terms, this is the arrangement of plates. You can see that the plates, ocean plates, are joined up, and there's a sort of a continual track of rift zones. And so you can go from any mid-ocean ridge to any other mid-ocean ridge by following the network along. And that the continental plates are essentially drifting apart because of the plate motion. Okay, so we've got these plates, and then there are plate boundaries. And as it happens, there are 3 types of plate boundary. There are plate boundaries that are divergent, and that's where a new plate is forming, and these plates are drifting apart. There are convergent plate boundaries, where the plate boundaries are coming together. Then there are transform plate boundaries. We already talked about what transform plate boundaries are. Divergent plate boundaries occur where the new seafloor is being spreading and where continents are rifting apart. So these are the kinds of plate boundaries that are divergent. Convergent plate boundaries, on the other hand, can be where any 2 plates are coming together. If we think about ocean plates and continental plates, there are 3 types of convergent boundaries. Ocean to continent, ocean to ocean, and continent to continent. And these three types of convergent plate boundaries have very different characteristics. So here are the basic ideas of divergent boundaries. This is ocean plate drifting apart. This is a convergent boundary where ocean crust is meeting other ocean crust, and these are transform faults. Let's see. So the overall idea, let me see here. Skip past this. So the three types of convergent boundary are ocean to continent. And when the ocean crust meets the continental crust, recall that the ocean crust is denser, about 3 grams per cubic centimeter for the basaltic crust versus about 2.7 grams per cubic centimeter for the granitic continental crust. So this denser material can't ride over the less dense material. And it's, we're thinking about giant formations and giant things, but that fundamental physics applies. And so when the two boundaries meet, the lithospheric plate, the ocean plate, ends up subducting, going under the continental crust. Now you might ask, what is the energy that's forcing these two plates together? Why don't they just stop when they meet? And there are two forces that apply. One is the spreading force, the new crust forming at the plate boundaries, at the spreading centers. So that's pushing on the ocean plates. And then the other force is the force of gravity, which is pulling the ocean plate down into the asthenosphere past the continental crust. So this is a subduction zone. Subduction zones are prevalent, particularly in the Pacific Ocean. So the Ring of Fire area of high seismic activity around the far western edge of the Pacific Ocean is caused by a series of subduction zones where Pacific plate is subducting under Asian plate. Okay? Well, so that's a ocean to continent type of convergent boundaries. What happens if an oceanic plate drifts into or is pushed into another oceanic plate? Well, in this case, you have two plates of equal density. They can't go down. So what happens is they go down together and they wrinkle downward. And with this downward folding, you get a crease known as a trench. And so these are deep ocean trenches. So the deepest places of the ocean are places where two ocean plates are coming together. And as they come together, they fold together downward. And this crease in the sea floor forms a long, narrow, very deep portion of the ocean. So the deepest oceanic trench is the Marianas Trench, which is about 11,500 meters deep. And there are other deep trenches. There's a deep trench in the Caribbean, which is about 8,000 meters deep. So wherever you have convergent ocean boundaries, you end up with a trench. Well, the opposite situation occurs when two continents come together. When continents meet, neither one can go down. And so what happens is that the two continents wrinkle together at the boundary. And this wrinkling process thickens the continent. So as it thickens, of course, that makes a larger portion that can float above sea level. And this collision results in a mountain range. So three types of convergent boundaries. Get a subduction zone. There are typically trenches along subduction zones. I guess I should add that as this material goes down, the sediments and other ocean floor material is rubbed against the continental crust. And this motion creates a great deal of friction and heat, and has the result that there are eruptions, volcanic eruptions on the continental side of the subduction zone. And so typically you'll find volcanic areas on the continental side of the subduction zone. North America, an example of that process can be found along the Pacific coast, where we have active volcanoes on the, where the Juan de Fuca Trench, where the Juan de Fuca Plate is colliding with the North American continental plate. And so Mount St. Helens, many of the active or potentially active volcanoes in North America are this type of continental arc volcano. Where two ocean crusts meet, again, you have this ocean material, crustal material being dragged down, and there is again heat being created and volcanic eruptions that are occurring. But because you have an ocean covering this, these aren't perceived as a mountain range, they're perceived as a series of volcanic islands. So typically on so there's one of the ocean crusts is going deeper than the other, and on the back side of this trench they'll have a back arc basin and a series of volcanic islands, and so that's another indication of this process. And then finally, where two continental crusts are coming together, that forms a mountain range. And an example of a mountain range formed by the collision of two continental plates can be found in the Himalayan mountains. The Himalayan mountains are some of the most recent mountains forming on Earth, and they began forming about 70 million years ago when the Indian subcontinent collided with the Asian continental plate. And this collision pushed up the Himalayan chain and created what are the present highest mountains on the planet. So these are the three types of convergent boundaries. So we are now in a position where we can renew the evidence for the theory of plate tectonics. So we have hotspots, islands of volcanic islands that form because the underlying oceanic plate is in motion. We have mid-ocean ridges, which are continuous seams in the seafloor, where new ocean crust is forming, where it's spreading apart. And we have transform faults along those mid-ocean ridges, which confirm that this process is ongoing and that produces durable results in the characteristics of the transform faults in the mid-ocean ridge. The characteristics of the seafloor, both its bathymetric shape and then the radioactivity for age dating, the magnetic properties of the rocks, these are all lines of evidence that confirm this overall theory of plate tectonics. And the final thing we're going to talk about in our review of plate tectonics and the evidence for that is hydrothermal vents. So Tuzo-Wilson proposed his theory, sort of put it all together in the late 1960s and put it out there. And again, just like with Wegener, he was not met with universal acceptance. In fact, there were many prominent scientists of the day that doubted or disbelieved the theory of plate tectonics. And there was a great deal of controversy, scientific controversy, throughout the 1970s, where our scientists argued back and forth about different explanations for the lines of evidence that were being put out. And so this was the condition that occurred in about the late 1970s. And as I said in our lecture on Tuesday, what was happening at this moment in time, scientific history, was what's known as a paradigm shift. What is a paradigm shift? Well, a paradigm shift, the concept of paradigm shift comes from Thomas Kuhn. He's a physicist and also a historian of science. And he proposed the idea that paradigm shifts were moments when scientific analysis of existing evidence suddenly changed. For example, and this is an analogy that actually comes from Kuhn's original paper. If you look at the picture on the right-hand side of the screen here, you can look at it in two ways. You can either see a duck with its bill facing to the left, or you can see a rabbit with its snout facing to the right. And so people will have different perceptions in looking at this. But if you're looking at it in one way and suddenly realize that this image that you've interpreted as a duck could actually be seen as a rabbit, that represents a shift in the way that you are thinking, or that your brain is processing the evidence that your eyes are providing. And so Kuhn used this analogy to explain how human understanding changes when scientific discovery and scientific thinking causes us to reevaluate the evidence that's available to us. And the concepts, the examples of paradigm shifts that have occurred in scientific history include the heliocentric system. So prior to Copernicus and Kepler and Newton, the idea was that the Earth was at the center of the universe, and that everything revolved and orbited around the Earth. And it was possible actually to build up systems that explain the motion of the celestial bodies in terms of a system where everything was orbiting around the Earth. And in fact, the whole idea of Ptolemaic theory or Ptolemaic interpretation suggests that there were these different ways of explaining the retrograde motion of the stars. So the example there is that if you're assuming that everything is orbiting around Earth, that would include the planets like Mars. But the planets are not orbiting at the same speed as the Earth is orbiting. So sometimes they appear to move one way across the sky, and then they'll appear to move the other way across the sky. Well, that can more readily be explained if we think that everything is orbiting around the sun. But if you have the concept that everything is orbiting around the Earth, then you have to build up a story to explain why Mars suddenly reverses its direction as we track its motion across the heavens. And so the scientists or natural philosophers, I guess, in operating under the Ptolemaic system before the Copernicus and Kepler, proposed that Mars performed little loops and curlicues in its motion. And that explained it, but it really wasn't a very good explanation. Another example is Newtonian physics. And so Newton explained the motions and orbits in terms of the gravitational attraction between celestial bodies. And so that the Earth was being attracted by the gravity of the sun, and that the interaction of the Earth's gravitational force and the sun's gravitational force produced an elliptical orbit, which kept the Earth on a path orbiting the sun in a slightly elliptical sense. And that all the other planets had to obey similar principles of gravitational attraction. So Newtonian physics put together a giant clockwork of the solar system that did a much better job of explaining the motion of Mars across the heavens, for example. Another example of a paradigm shift was the idea that DNA provides a code by which life forms can reproduce themselves with very little error rates. And so prior to the discovery of the DNA molecule and the realization that DNA occurs in all cells, scientists and thinkers didn't have a good idea for how it was that, that animals and plants can reproduce more or less exact copies of themselves, but that there can be slight changes in these copies over time that result in the establishment of new species. Well, once DNA is understood to be part of the structure of all cells, then we have a mechanism to explain how life is both able to reproduce itself and how gradual changes can be introduced. Well, the idea of this paradigm shift allows us to see evidence in a new and better way, but science and scientists resist paradigms. They resist paradigm shifts. And so when Tuzo Wilson proposed his theories and the evidence started coming in, looking at all the different ideas, it was clear that, yeah, plate tectonics might explain a lot of these concepts, but that scientists were still reluctant to abandon the theory that the Earth was shrinking as it cooled off. Well, the final bit of evidence came from the discovery of hydrothermal vents. And I'm going to show you now a video to explain hydrothermal vents. Hydrothermal vents are places in the ocean floor. They occur not just at spreading centers, but the initial discovery was at spreading centers. And let me switch over to this movie, stop sharing my screen, and I'll share a different screen. And hopefully this will play and you'll all be able to see it.
In 1977, the discovery of hydrothermal vents releasing hot, mineral-rich water at the bottom of the ocean changed our understanding of the world as we know it. We had thought all life depended on sunlight to survive, but these vents showed us we have so much more to learn. Today, hydrothermal vents of all kinds continue to be found in areas of known volcanic activity across the ocean.
There it is. You're in it, man. Really?
The phenomenon continues to mesmerize scientists and ocean enthusiasts alike.
That's amazing. You get to do this sort of thing once in a lifetime. Okay. Once in a lifetime. That's brilliant. Brilliant.
The first discovery of hydrothermal vents in 1977 was actually on 35mm film. Geologist and oceanographer Dr. Bob Ballard was part of the research expedition that made history. Reports of dramatic spikes in water temperatures from a small area of the Galapagos Rift led Ballard and his crew to send a still camera down to investigate the area. Stunned by the unexpected findings captured in the photos, they deployed the Alvin submersible the very next day to explore the region firsthand. To their surprise, they had discovered an entirely new ecosystem, thriving with giant tube worms over a foot long, as well as many other life forms. Up to that point, all life was considered dependent on sunlight for photosynthesis, the process by which plants convert energy into a usable form of sugar. But this life was at depths far beyond the reach of sunlight. The discovery rocked the scientific community, prompting biologists to return to the site to investigate how these life forms were able to survive. They realized that the organisms were clustered around structures emitting plumes of superheated water packed with chemicals. Though toxic to humans, the chemicals provided nutrients that bacteria could convert to energy, much like plants convert sunlight during photosynthesis. This process of converting chemicals to energy became known as chemosynthesis and redefined science as we know it. The structures came to be known as hydrothermal vents for the superheated water they emit. Hydro, meaning water, thermal, referring to temperature, and vent, indicating the release of matter. Along volcanically active areas such as the mid-ocean ridge, water seeps into the Earth's crust through cracks and fissures and becomes superheated by hot magma within the Earth's layers. As it boils up to be released on the ocean floor, the water picks up dissolved metals and minerals along its journey. And finally, the water exits the Earth's oceanic crust, creating vent structures. The characteristics of hydrothermal vents vary depending on the specific metals and minerals in the water they emit. Vents known as black smokers emit water that appears as a thick black cloud because it is rich with sulfur-bearing minerals. As the dissolved minerals and metals encounter the freezing ocean water, they solidify in layers, forming massive structures called chimneys. Lasers, spaced at about 10 centimeters apart, almost 4 inches, help scientists determine chimney size. Some chimneys have been spotted at heights of up to 18 stories tall. In contrast, white smokers are characterized by the barium, calcium, and silicon they contain. Some vent fluids aren't characterized by a specific color, but can be identified by the shimmering water they emit due to the stark difference of water temperatures. And other vents simply emit carbon dioxide in streams of bubbles like carbonated soft drinks. Don't be fooled by what may seem like gently flowing water. The water pressure is so great down here that what appears to be a gentle outpouring of water would actually be a violent eruption if it were on the surface, much like geysers we see on land. The vent fluid can be up to 750 degrees Fahrenheit, 400 degrees Celsius, but it does not boil because of the immense pressure. It's amazing that life can thrive under these conditions in the midst of scalding hot water, immense pressure, and near freezing ocean depths. The discovery of new geological and biological phenomena like this drives explorers every year to further investigate what else lies deep within the ocean.
Okay, so that was a nice video of the discovery of hydrothermal vents and their significance for the theory of plate tectonics. And so it's fair to say that there was a total shift. So people who, scientists who had rejected initially or were skeptical about the theory of hydrothermal vents, when the results came back from the Alvin expedition, when Ballard and James Corliss, who is the chief scientist on the original expedition, when they published their findings, that was sort of the final nail in the coffin, or the final convincing evidence. And very quickly, the theory of plate tectonics gained wide acceptance. So this Alvin submarine sort of gave us a window into this process, and that window into the process was the final bit of evidence that convinced folks that this was occurring, that plate tectonics was a viable theory. So we can go back and review now what the overall theory of plate tectonics is. It suggests that the Earth's crust is divided into lithospheric plates, continental and oceanic, that the plates are floating in quotes, on the asthenosphere. The asthenosphere is ductile, it's moving, it can change its size and its shape and its volume without fracturing. Whereas the lithosphere, when it moves, it has to break apart and there's massive seismic energy released. So the ocean crust, the ocean plates and the continental plates are floating on this asthenosphere, and they're gliding along on this boundary between the brittle and the ductile material. And there are active geologic features at these plate boundaries. We've reviewed a bunch of these different features. There are subduction zones, a mountain range formation, ocean trenches, transform faults. All of these observable features fit together in the theory of plate tectonics. What's powering all this, what's driving all this, are convection currents, so that as the immense heat of the interior of the Earth is released, it sets in motion convection cells, sort of roughly circular motion of rising hot material and sinking or descending cold material. And that this motion over incredible sizes and vast scales is what ultimately drives the process of plate motion. So plate movement is powered by these convection currents. The seafloor is spreading, and the downward pull of the plate's leading edge is what drives subduction. So this is the fundamental theory of plate tectonics, and this is represented a paradigm shift in many ways of thinking about the ocean. We're primarily focused on ocean geology right now, and I'm trying to understand how plate tectonics produces the ocean basins that we can observe in the present day. But with the confirmation of plate tectonics and that theory, there were many other scientific understandings that had to shift to accommodate this new theory. For example, we've already heard in the video how the recognition of the chemical energy that was continually being released with this hydrothermal material could actually support life forms which scientists and regular people had not previously thought could exist before the discovery of hydrothermal vents and associated chemosynthetic organisms and communities. Another area of scientific thinking that was transformed by this new idea of plate tectonics was Earth's climate. And so, prior to that, we sort of thought of climate as a result of these dynamic processes of wind and ocean currents, and meteorology had a good understanding of why the atmosphere was in motion and how the atmospheric motion interacted with the land and the mountain ranges and the ocean, etc. But the idea that there had been long-term changes in that in Earth's climate was sort of really just coming together. And as it turns out, if you have a different arrangement of continents on the ocean, on the Earth's surface, this is going to produce very different types of planetary climate. And there are reasons for this. The Earth is being heated to the greatest degree along the equator. And we'll come back to this concept many times when we look at ocean currents and atmospheric circulation. But the area of greatest heating on the Earth is around the equator, where the incoming solar radiation has the most direct path to the surface of the Earth. So if the Earth is being heated around the equator, it's being cooled around the poles. So there's a transfer of heat from the equatorial area, from low latitudes, towards high latitudes. Well, this heat, as we'll see when we look at the properties of water and the circulation of air, this heat, transport of heat, depends on or is affected by the kinds of land barriers that it encounters. And so if you have an equatorial seaway, in other words, an open ocean connection all around the planet at the equator, that means that heat is transferred less efficiently from the low latitudes towards the high latitudes. And so a planet with an open, or Earth with an open equatorial seaway would be warmer than a planet in which there were continental barriers across the equatorial path. And so, if we think about, and likewise, if there's a barrier at the equator, but there are open passageways in the high latitudes, that would produce a different set of circumstances. So by rearranging the continental boundaries, or or the barriers formed by continents, we know we don't just change the shape of the oceans, we change the processes by which Earth releases its heat or loses its heat. In doing so, we fundamentally change the climate. So if we look at the formation, so we've said that the Pangaea broke apart. With the breaking apart of Pangaea, we would have had very different arrangements. And so we would have gone from a world where there was basically a barrier, a continuous barrier from north to south. And then as that broke apart in the mid-Jurassic, we've got a sort of a slice world. And then in the Cretaceous, we would have an actual, about 100 million years ago, we would have an actual equatorial seaway. And so we would expect, just looking at this, that the mid-Cretaceous period would have been much warmer than the late Jurassic period. And in fact, various lines of evidence seem to infer that this is the place. If we step ahead to the mid-Tertiary, about 30 million years ago, well, there's still an opening for circulation through the Isthmus of Panama has not yet joined up the North American and South American continent. So there's ocean circulation through this region. So this would be a warmer world than the present configuration of planets, where the ocean basins are separated by these very substantial north to south ocean continental barriers. And in fact, the last 30 million years ago, since the isthmus closed up, have been generally described or generally characterized by a cooling of the planet. And so we're coming out of an ice age, so that the cooling of the planet results in large ice sheets that cover large regions of the North American continent, which is the area most affected by this opening and closing of the vent. These glacial covers advance and retreat according to other forcing processes. So the theory of plate tectonics also gives us a window into long-term changes in Earth climate, and it teaches the fundamental lesson that the Earth is not a static entity over time, that its fundamental conditions, the fundamental arrangement of ocean basins and of life forms that depend on these ocean basins, and climatary cycles that depend on the transfer of heat, are changing. The ground rules are changing in fundamental ways. And we'll get back to this theory of oceanic circulation and so forth as we move ahead with the course. But that basically ties up the theory of plate tectonics. All right, let me stop sharing, and we'll have time for questions. I've covered a lot of material on Tuesday and today. I've spun through a lot of stuff. Let me take a few minutes to answer some questions, if there are any questions from the class. And after that, we'll get into our breakout rooms, and I'll ask the different teams to have a look at the suggested paper topics, suggested research topics that are present in the that you can access in the Canvas site. Questions, please. It's hard for me to talk to a screen here, and I see names and everything, so it really helps me if you ask questions and come back and say what you're thinking about this, or what you don't understand, or what you find particularly interesting. So please give me some questions. Let me know that you're hearing this and that I'm getting through. Hello?
You had said earlier that the places stopped moving apart in one area. What sort of things would make that happen?
I'm sorry, say that again, Joseph?
You showed a picture of, I think it's in like Jordan or something, where the plates stopped moving apart.
Right.
What would make that happen where they would stop moving?
Yeah, I think the idea is that, along the axis, so this is exactly what we're talking about right there. And so this is the triple junction, and the East African rift valleys were initially part of that three-pointed star that would have formed when the mantle material broke through. Well, the mantle material is trying to release heat and trying to allow this generation of new oceanic plate to release its heat. Well, you know, if the spreading is successful along the two axes of this three-pointed star, then most of the dissipation and most of the energy can be released there. So it's more efficient. You know, one idea would be that it's more efficient for motion to continue, for seafloor generation to continue along the two axes that prove to be the most active. Does that make sense?
Okay, so it can like stop on the third one then.
Yeah.
And just continue on the other two. Okay, that makes sense to me.
Yeah, yeah, and by all means, try this experiment when you have an orange. You know, when you have an extra orange, take that peel and poke through it, and you'll see that the most efficient way of breaking through a spherical surface is to form that three-pointed star. Okay, other questions?
Sorry if I missed this earlier, but I understand that the the placement of the plates and the faults and everything influences the climate, but I was wondering how exactly that happens. Is it like is it because of like the vents like raising the temperature of the ocean, changing the currents, or something else?
Well, we can think of the Earth as a machine. I don't know. The Earth is responding to the input of energy from the sun. It's also responding to the input of energy or the release of energy from the geothermal energy of the Earth's center. But the atmosphere and the ocean have to respond to the heating by the sun. Okay, so if we think about heating a bath or boiling water on a stove, the release of that heat is going to set the fluid in motion. Different ways. We can think of, if you have a heater in the middle of a room, the hot air is going to rise and that over the heater, and that's going to set in motion, drafts and currents of air within that room. That makes sense, right? So we've got this this planet, this globe, which is being heated most intensely along the equator. So the sun, all Earth's energy is arriving at the sun. It's arriving, the density of energy and density of sunlight is equally distributed across space, but the degree to which it heats the surface depends on the angle of the Earth's surface to that incoming solar energy. So if the angle, at the poles is less than the angle at the equator is going to be warmer. Does that make sense? So we've got a differentially heated planet. And what's responding most dynamically to this difference in heating are ocean water and the atmosphere. And so that heat is going to be transmitted, is going to move, generally speaking, in broad terms, from the warmer area to the cooler area. Okay, so within this envelope of ocean and atmosphere, the fluids are going to be generally translating heat upward to the cooler areas. And so I made the analogy of, suppose you had a large warehouse with a single, very hot stove in the middle. Okay, so air would be heated on that stove and it would be rising up from that stove, would be hit the ceiling and it would spread out, and there would be large scale circulation patterns of the air within that big warehouse area. That makes sense? Okay, well, suppose you put a wall in that area or a partial wall that went part way up to the ceiling. You could see that the air, that the motion of that air would be deformed and would be deflected, by the presence of that barrier. And so, in analogous terms, in terms of a big picture, that's what happens when we have different arrangements of the continental barriers across the surface of the planet. Different transport different mechanisms and different patterns of heat transport can take place across the planet. Does that make sense, Joshua?
I think so. So basically you're saying basically the shape of the ocean and how much water is near the equator would change like the direction of like the air currents moving, like and cooling, like where they're going to move when they're cooling down.
Yeah, exactly. I mean, the heat of the sun sets in motion the water in the atmosphere, right? And we can just understand from simple observation that if you heat something up, the hot is going to try to move toward the cold. There's going to be a gradient of motion, put in motion, set and trained by the energy input of the hot stove or whatever it is. Okay, but that the ocean is remember we talked about the basketball world. Well, the ocean and the atmosphere are this thin film, and so the heat can't be transferred downward. It can't really go upward. It has to move in across the surface of the globe, and that as it moves, it encounters barriers, and these barriers are continents. Well, if the continents are changing their orientation, we're going to have different regimes of heat transfer. Some of them will result in higher temperatures than others. Okay.
Thank you.
Sure. Any other questions? How many people had heard of hydrothermal vents and black smokers and tube worms before? Everybody?
I never heard of that. That was very interesting.
Oh, cool. Okay. Yeah. Well, I think it's interesting too, and it's one of the things that I've really enjoyed learning about. It's one of the things that really captures our thinking, and it's it was so unexpected and it was so dramatic, and it really changed the way we think about life on Earth. Not just this idea that that everything wasn't dependent on photosynthesis, but that there were possibilities of symbiosis and relationships between organisms that nobody had really started imagining until they had the example of tube worms and mussels, etc., from hydrothermal vents. And I like this subject, so I'll talk more about it as we get more into ocean biology. But just as a little preview into that topic, we can see that the discovery that life didn't necessarily depend on the sun, that life could also evolve in the presence of chemical energy, really allowed us to think about how life might have originated on the planet. And so, now it's pretty well thought that life evolved in the oceans, probably near hydrothermal vents or some places where chemical energy made it possible for microorganisms to exist. Other questions? All right, well, let me do one other thing here. I will bring up the so I'm going to share my screen again. Let's see if I can get that. And I'd like you to take a look at the suggested term paper topics. I'm going to open up the breakout rooms, and I'd like the different teams to just have a look through here and have a talk about what we talked about in the lecture today, and then start brainstorming together about what your term paper topic might be. And so I've put down some different areas here: physical oceanography, geological oceanography, biological oceanography, chemical oceanography, oceans and climate change. So these are all areas where you might be able to put together a project that your team can work on throughout the semester. And so what I would suggest is that you don't sort of pick on one, that you pick several, and then sort of go by a process of elimination, do a little preliminary research and thinking about these topics, and then try to settle over the next couple of weeks onto a topic, because there'll be a milestone due pretty soon, and you'll need to be looking at that. Okay, so what I'm going to do now is open up the breakout rooms. And you should all be able to get into breakout rooms. Hopefully we've got it all sorted out so that the proper emails are associated with folks. You've all picked names. Right now they're just identified by number. And go ahead and get into your breakout room. Start looking at those topics, and we'll conclude the class in about 10 minutes. But let's go ahead and look at that. All right. So go ahead and join your breakout room if you haven't already. They're all open now. And then have a look at the term paper, suggested term paper topics. Okay, Carrie, I made you co-host. I'm going to assign you to a room. Hopefully you'll be able to go to the other thing here. So Carrie, I'll assign you to group 11.
Okay.
And I will go to group 1. And I've got somebody here who I can see is calling in by phone. Could you please unmute your microphone and identify yourself? Hello? Who's joined by phone?
Rules, but we could also do I don't know, any of them in biological.
Oh yeah, so you
Sound
guys
good.
want to dial it down to biological instead of any of the other ones?
Don't close off. You might find that you like some of the other material as well. And don't everybody try to work on coral reefs, because I've seen so many projects on coral reefs over the time that there's a very high bar for coral reef research projects. So just keep that in mind. You're welcome to choose coral reefs if you want, but lots of people pick that. And there's so much more in the ocean that you can learn about. Or if you do want to do corals, we'll talk, and I can suggest some ways that maybe you could do something that would be more exploratory and more informative for you. Okay.
Okay.
All right. So just kick it around there. I'm going from room to room, seeing how everybody's doing, and so carry on. Hey, Nelson, do you need to join a room? Nelson?
So
Hi.
we can do the oil spill one. That one seemed like everyone was on board with that.
Yeah.
Or honestly, like we can do like narrow it down to the oil spills, or we can maybe like an approach to it would be maybe we pick 2 or 3 of the hazardous materials that are like there and give an example for each and how like the different effects of each hazardous episode.
Yeah, I like that idea, Isabella.
Like brainstorming, let's just write it down.
Yeah.
Yeah.
The same with like gas hydrates. We can do like specific like gas hydrates that are like CO2, blah, blah, or like whatever, and then talk about how those affect the climate.
I'm gonna add a page in our Google Doc so we can write down some of these notes as we're brainstorming. So yeah, feel free to hop on that and to add stuff to this as we're coming up with ideas.
You guys look like you're doing great. Oil spills are good. I mean, I think it's a good idea to keep it broad. And then, you know, as you do a little research and dig into it, maybe, you know, you'll see, oh, hey, this is where we want to go. This is the most interesting. But, you know, there's also sort of overarching themes, you know, so make sure that you can talk about climate, you can talk about impact to society, you know, that you're able to find a wide range of primary literature on the topic. And so that'll help you as you go forward. All right, just checking in. I'm going from room to room.
Thank
All
you.
right,
Thank you.
Sounds good. I'm good with
That
that.
sounds good to me.
Okay, I think we're missing.
Yeah, that sounds good.
They just got here. Oh, it's okay. I'm so sorry.
Yeah, hello, I'm just going from room to room. So you're missing one person, I guess, or?
Yes, missing one person.
Okay.
Yes, I think so.
Yeah, well, it's a good idea, you know, because we'll be doing lots of this group work. And so it's a good idea to, you know, have an email list and, you know, shared Google Docs and that sort of thing. So you can, you know, you can stay in touch with each other. But people do have to, you know, it happens that they're not present or whatever. What I really want is if somebody has to be absent, that they let their teammates know so that there's no impact on handing in assignments or that kind of thing. What sort of topics have you talked about?
We were kind of thinking, like, let's see, the threats to like coral under global climate change, because a lot of us in high school had a lot of experience with that.
Okay. Well, I'll tell you that I've seen lots and lots and lots of projects, research projects on corals, coral reefs. And so I have kind of a high bar for that. So just be aware, you know, that if you're going to take on corals, we need to talk carefully so that, you know, I make sure that there's, you know, a lot of scientific rigor in how you the topics of the area that you choose to research. Not that you can't do corals, but, you know, maybe do deep sea corals or, you know, corals, you know, ancient corals or something like that. There's ways to approach that will, you know, provide for a lot more scientific rigor and a lot more diversity. And, you know, we want to go to the next level from a sort of a high school report on corals to, you know, really understanding the science, the scientific questions and discoveries that you know, that come from that topic. Make sense?
Yes.
Okay. Gotcha. All right. I'm just going from room to room. I'll check in a minute. Hello. So this must be the sassy sea slugs.
Yeah.
Yes.
How are you doing? What sort of topics have you figured out?
We're thinking of something with either coral reefs, oil spills, or the topic on whale sounds. Seemed pretty interesting.
Okay. Yeah, lots of people want to do coral reefs. I think just for my own sanity, I may sort of limit the number of coral reef research projects for the class. And this is the fourth breakout room I've joined, and all of the other breakout rooms we're talking about coral reefs. So I don't want everybody to do coral reefs. There's a lot more to ocean science than just coral reefs. So I have kind of a high bar there. So
Okay.
Diversify. I encourage you to diversify. And there's lots of material that you can have. All right, I'm going to have to close the breakout room because we're almost out of time. But good to see that you're all working together. Okay, looks like we're getting back together. Let's see. Okay, so that was class for Thursday. I'll put the, you all saw the recording of Tuesday's class, and I will have recorded today's class, and I'll put that on the Canvas site. You'll be able to access that. And I guess I went around to several breakout rooms, and I think Carrie was also circulating. Carrie, were you able to go from room to room this time?
Yes, I could.
Okay, great. All right, so a couple of the people, all three or all four of the breakout rooms teams that I visited were talking about coral reefs as a potential research topic. And what I told those teams was that not everybody can do coral reefs, number one. Number two, Carrie and I have seen lots and lots of research topics on coral reefs, not just in oceanography, but also in our issues in environmental science class. So
Same with plastics.
Same with plastic. So we have a high bar for the kind of scientific rigor that we want to see if a team takes on coral reefs or plastics. So think about that. And if you decide, so I'm going to say right now, that I'm only going to allow one team to do coral reefs and one team to do plastics. What do you think, Carrie? Is that being too prescriptive, or it'll make for a more interesting presentation as the groups begin sharing their research topics. So if two groups really want to do corals, we'll get together and we'll figure out a way to divide that. But fundamentally, I'd prefer that you consider some other options. And there's so many other things going on, you know, chemical oceanography, dead zones, paleoceanography. There's lots of material here, and other topics will occur to you as we go on. Okay. Any other questions for today before we end? Nope. All right.
Do we email what topic we want to you, like our group?
Yeah, we'll do an assignment. That's a milestone. So there's a milestone picking a topic, and I think that, you know, Carrie, do you remember when that milestone is due? It's coming up.
We don't have it in the modules yet.
It's not in the modules yet.
24th, according to Canvas.
February, yeah. So it's on Canvas. So yeah, you'll have that. You have to come up with a, you know, with an actual assignment, and you know, there's some specific requirements there. And yeah, we'll get that milestone project. Yeah, January 24th. So that's the week from Sunday. So you'll have 2 more class sessions and whatever you can put together, and we'll put that milestone into the assignments for the week 3 module. Okay.
Okay, thank you.
All right. Okay, everybody, I'm going to end the class. And actually, I'll keep it open for a few more minutes in case anybody wants to hang around and ask questions. But you're free to move on, and I'll see you on Tuesday. And of course, you can always email or you know, get in touch, and we'll get back to you. Okay. Bye, everybody.
Thank you.
Thank you.
Bye, thank you.
Thank you.
Sure.
Hey, Professor, can you hear me now?
Yeah, I do. So Zoe has a question, and did you have a question too?
I did have a couple questions. I'll let Zoe go first.
Okay, so you're on the phone, right?
Yes.
Okay, that's tough. Do you not have internet connection?
I do, but I think because I wasn't registered, I think whatever that process was keeping me caught up, because like I would click the, you know, like enter the code for the, because I have it on my phone, and it would just wouldn't, it kept asking me to switch accounts, and even when I tried entering all the credentials, it just wasn't working out.
Okay. All right. Well, why don't you and Carrie get together and try to sort out because you really want to be following along, you know, either on a laptop or a tablet or something.
Is this
Yeah.
So, yeah, can you identify yourself? Sorry, we don't know who you are exactly.
Farhan Ahmed.
Okay. All right. Well, Carrie, you'll get together with Carrie and talk about that.
Okay.
And Zoe, what was your question?
So like, sorry,
No worries.
my group kind of talked about like doing ocean acidification kind of more pertaining to the runoff situation from Midwestern states into the Gulf of Mexico.
Okay.
And we kind of wanted to do coral in there just in like how coral disease is being affected by that, but we didn't want to do the whole thing as coral. Would that be okay?
Okay, well, you've got a couple different processes that you're mixing together there. So the process of ocean acidification is a result of carbon dioxide being absorbed out of the atmosphere and lowering the pH of the ocean water. And so that's a sort of a global phenomenon that's happening because we're burning fossil fuels and putting so much CO2 into the atmosphere that some of that CO2 ends up in the ocean, dissociates and forms this weak acid. And so that lowers the pH, and that has an impact on corals, on shellfish, on calcareous plankton, and many other organisms. So that's sort of one process. The runoff from the land, what that produces is not ocean acidification, but that produces eutrophication, so that the increase of nutrients causes blooms of algae and other microorganisms, and that results in high biological oxygen demand and the so-called dead zone. So that's a separate process from ocean acidification. And both ocean acidification and hypoxia can affect corals and many other organisms. So part of the process of picking a research topic will be kind of getting straight in your, among your team, exactly where you want the topic to go. Does that make sense, Zoe?
Yes, absolutely. I just wanted to make sure like it would be okay if we used a much broader topic to kind of talk about the smaller topics.
Sure. Yeah, but you'll have to think of a way of tying that together. So, because if you get very broad, then it's sort of hard to, have a well-structured report or a well-structured presentation.
Okay.
Okay, and we'll totally work with you guys on that to come up with that. Okay.
Thank you so much.
Sure. All right. So I'm going to go ahead and end the session today.